Hello class. So on this video, we're going to start on section 6.3 in the book. So let me write that here. So 6.3 in the book. The topic that we're going to cover is the topic of step functions. Now, as I mentioned in the previous video, the real power for us right now with the Laplace transform is that it's going to allow us to deal with finding solutions to non-homogeneous linear ODEs in which the g of x, right, whatever's on the right-hand side, is not necessarily continuous, but piecewise defined, so piecewise continuous. Right? The Laplace transform is going to give us a way to solve those ODEs. Right? The way we're going to do it is by simplifying those integrals by defining this step, or also known as a Heaviside function. I'm just going to call it step function because it's easier, but it's also called a Heaviside or Heaviside. I think it's Heaviside function. Right? But that's going to be the idea. We're going to work or build to an easy way to calculate Laplace transforms of piecewise functions, but we already have a method of doing that, but we'll work on a more efficient one, and then we're going to see how we can apply it to g of x functions that are not continuous, just piecewise continuous. So let's start defining what a step function is. Right? So a unit step function or a Heaviside function is a function which we're going to label as u sub c of t of the form, right? U sub c of t equals 0 for all t values less than c, and 1 for all t values greater than or equal to c. Right? So a very simple definition. Right? If you look at the graph of what this function looks like, and again, we only consider values of t greater than or equal to 0. I'm just going to graph that. But later, we're going to see that this also works for t less than 0. Doesn't matter what it is. But for us, for right now, just for this picture, let's just consider t values greater than or equal to 0. So what does this look like? So let's label c here. So for t less than c, this function is 0. So it's something like that. And then at t equals c, it jumps all the way to 1. So not including 0 there. Then it jumps to 1, and it continues like that forever. So a very simple piecewise function. Or just 0 and 1. Now, you can think of this piecewise function as, and this is how I like to think of it, as turning off and on a switch. Right? So for example, you can think of, for t less than 0, right, the switch is off, and then at t equals c, we turn the switch on, and we leave it on. So that's how I like to think of it. Another way people think of it is as for t less than c, we have a certain state that is turned off, and at t equals c, we turn the state on. Right? So either way you want to think of it, it's fine. But I think thinking of it this way is the most enlightening. Right? So for our purposes, I'm going to think of this as for t less than c, I have a switch off, like a light switch is turned off. And then at t equals c, I turn on the light or I turn on the switch, and then I leave it on for all t greater than or equal to c. Now, let's see an example. Right? Let's sketch the graph of h of t equal to u sub pi of t minus u sub 2 pi of t for t greater than or equal to 0. Right? So first, let's write down what these functions are. Right? So they're easier to graph. So u sub pi of t is by definition 0 for, and so when considering t greater than or equal to 0, so for 0 less than or equal to t less than pi, right? And then at pi, it jumps to 1. Right. Now, u sub 2 pi of t, it's the same thing, but it jumps to 1 at 2 pi. So 0 for all 0 less than or equal to t less than 2 pi, and then it's 1 for t greater than or equal to pi. Okay, so let's remember, we're trying to graph the difference of these two. Right? So we can just see what's going on each interval. Okay, so here I see 3 subintervals that are mattering. Right, we're going from 0 to pi, right? And then something happens. And then we're going to from pi to 2 pi, right? Something happens there at 2 pi. And I can just have 1, not including. So let's do it like this. Right? And then from 2 pi to infinity, we have something else. Right? So just looking at the problem, right? These are the 3 intervals in which some things are changing. Right? right? These functions are going to change at pi, at 2 pi. So we consider those 3 intervals. Okay? So let's see what the function is on each subinterval. So on 0, so on the interval 0 to pi, what do we have? Well, u pi of t in this interval is 0. Right? U sub 2 pi of t equals 0, right, which implies h of t, which equals their difference. Right? 0 minus 0 is 0. Right? And that's it. That's what we have on the interval 0 to pi. Both are 0. Now, on pi to 2 pi, something happens, right? So what's going on here? Okay, on this interval, u pi of t is what? On this interval, it is equal to 1, right? Because u pi of t becomes 1 at pi and stays as 1 for the rest of the interval for up to infinity. However, u of sub 2 pi of t is still equal to 0 on this interval because it doesn't jump up to 1 until we reach 2 pi, which again, we're not including in this interval. Right? So in this case, what's h of t? It's the difference of these two, right? So we get 1. Right? Finally, on 2 pi to infinity, what's going on? Well, here, u pi of t is still equal to 1, right? Because this is bigger than pi. 2 pi is greater than or equal to pi, right? So it's still equal to 1. But now, u sub 2 pi of t is also equal to 1. So when we take their difference, right, h of t is going to be 1 minus 1, which is going to be 0. Okay. So what does this function look like if we graph it? Right, and then we're going to label pi and 2 pi. Okay. So from 0 to pi, let me use a different color, blue. From 0 to pi, the function is 0. Then at pi, it jumps up to 1. And then at 2 pi, it jumps down back to 0. And it goes on like that. So this is the graph of h of t. And that's usually how you want to work with, if you want to graph a step function or a combination of them, you want to do it like that. Okay, look at the intervals which are defined in each separate step function, and then partition your interval into subintervals determined by those inputs, right? So in this case, we know that something happens at pi, so I want to go from 0 to pi. Something happens again at 2 pi, so I want to go from pi to 2 pi, and then we go from 2 pi to infinity. Okay? So that's the idea. Okay? Now, let me talk a little bit more about why step functions. Okay. So we already know how to calculate. Again, I mentioned before that the power of Laplace transforms is giving us a way to work with non-homogeneous linear ODEs in which your g of x or g of t, whatever input independent variable you're using, is piecewise instead of continuous. Right? So as I mentioned before, and we saw in previous videos, we already know how to take the Laplace transform of piecewise continuous functions. We just separate the integral into each subdomain. It's as simple as that. So why introduce step functions? Well, as I mentioned at the start of this section, the idea of introducing step function is to give us a more efficient and fast way to calculate the integrals, or sorry, the Laplace transforms of piecewise functions. Right? So us introducing step functions is going to give us a faster way of computing these the Laplace transform of these piecewise functions without having to use the formal definition. That's going to be the idea. We do it to make our life easier. Okay. Now, before I say that, first, you can easily compute the Laplace transform of u sub c of t, right, of a step function, just using the definition of the Laplace transform. Right. So if you have c greater than or equal to 0, right, then u c of t is going to be e to the negative c over s, right, for s greater than 0. And this you just compute by the definition. Right. Just divide your integral into subintervals. Right. Now, like I said, in general, we're interested in finding a faster way to compute the Laplace transform of a function that might look something like this. Now, how we look at this function, right? So it's 0 for t less than c, and then for t greater than or equal to c, you can think of us like switching on the switch, and now the function, it's not 1, but it's f of t minus c. Right? So in a sense, you can see how this can relate to step functions, right? Because something is off for t less than c, but for t greater than or equal to c, we turn that thing on. In this case, we're not turning on just the constant 1, but we're turning on the function f of t minus c. Now notice that f of t minus c just means that this is the function f, but shifted c units to the right. Right? That's what that transformation corresponds to, right? You learned this in college algebra, right? If you're subtracting to the input variable, then it's the same as shifting to the right how many units you're subtracting by. Okay? Okay. So think of this then, g of t, what is it doing? For t less than 0, where the switch is off, and at t equals c, we switch on the function f starting at t equals c.